Hello everyone, welcome to the class U18 PCAE 601 Finite Element Analysis. Myself, Mr. N. Kalaimani, currently working as Assistant Professor in the Department of Aeronautical Engineering, Bharat Ministry of Higher Education Research, Chennai. Today we are going to discuss the topic of plane truss analysis by finite element analysis. So, what is meant by truss? Truss is nothing but a group of structural members connected or welded together to carry your axial loads. It is generally classified two categories. One is plane truss as well as stress truss. If the truss consists of members are lying in the same plane or loaded in the same plane, then it is called as a plane truss. Example, roof truss, bridge trusses, as well as etc. The space truss, if the members connected in the truss are do not lie in the same plane, then it is referred as a space truss. This example is a electric power transmission tower as well as microwave tower. Then generally speaking, the structures are broadly classified two categories. One is statically determinate structure, another one is statically indeterminate structures. If it is a statically determinate structure, means all the internal force induced in the member as well as the reactive force from the support that can be analyzed with the help of static equilibrium equation alone, then this structure is called as a statically determinate structure. If it is statically indeterminate structure, means not only the static equilibrium equation, in addition to you have to develop stress strain compatibility equation to analyze the internal force induced in the member as well as reactive force from the support. Then it is called as a statically indeterminate structures. In this case, we have how to determine the static indeterminacy for a truss element or truss structures. So the degree of static indeterminacy can be calculated from this formula. I is equal to m plus r minus 2j, where m is nothing but number of members, where r is nothing but the reactive force from the support, j indicates joints. There are two types of static indeterminacy. One is whether the structure is external static indeterminacy or whether it is internal static indeterminacy. If it is external static indeterminacy, then I is equal to R minus 3, where R is nothing but the reactive force from the supports. Then it is a internal static indeterminacy, then you have to satisfy this equation m plus 3 minus 2j, where m is nothing but the members in the truss element. The j is indicates number of joints. Then one more determinacy is called as a kinematic indeterminacy. It means the minimum independent quantities required to describe the displaced shape of the structures. And the kinematic indeterminacy is equal to unrestrained degree of freedom minus restrained degree of freedom. So you just look at these given structures, how to find out your degree of static indeterminacy. The first thing is I have to calculate the degree of internal static indeterminacy. The formula is m plus 3 minus 2j. So where j is indicates joints, how many joints per given structures? We think that structure having 10 joints, that j is equal to 10. Then m is equal to number of members in the truss structures, where m is equal to around 17 members. Then we have to substitute this equation, and I will get the internal static indeterminacy value is 0. It means the structure is statically determinate internally. Then how to determine the degree of external static indeterminacy? The formula is R minus 3, where R is nothing but the reactive force from the supports. I have two supports. One support is a hinged support. It will offer two reactive forces. One is horizontal as well as vertical reactive forces. Roller support provide the vertical reactive forces. This means perpendicular to the roller, the reactive force will act. Therefore, the three reactive forces from the support, therefore 3 minus 3, then it will get zeros. Therefore, this structure is externally determinate structures as well as internally determinate structure. Therefore, your total degree of static indeterminacy, external indeterminacy plus internal indeterminacy. We add these two equations, finally we add m plus r minus 2j, where m is nothing but your number of members in the truss structure, where r is reactive force from the support, then j is indicates number of joints. When we have to substitute, we will get the degree of static indeterminacy 0, then this structure is called as a statically determinate structures. Now, how do you find out the kinematic indeterminacy? I already told that kinematic interdeterminacy is the minimum number of independent quantities is required to describe the completely displaced geometry of the structures due to application of your external loading. So here each joint having 2 degrees of freedom, one is horizontal displacement, another one is vertical displacement. Therefore, we have 10 joint. Therefore, then unrestrained degree of freedom 10 into 2, we have 20 unrestrained degree of freedom. But we have two support, one is hinge support, another one is roller support. The hinge support offer 2 reactive forces. It will be arrest that vertical horizontal movement of that particular nodal location. Then roller support will be arrest only the vertical reactive forces in this case. Therefore, 3 displacement is arrest due to application of your reactive force from the support. Therefore, the restrained degree of freedom is 3. The kinematic interdeterminacy is equal to unrestrained degree of freedom minus restrained degree of freedom. So 20 minus 3, we will get 17. If you know the 17 displacement quantity, then we can easily describe the displaced shape of the structure. Then look at this structure. Here we add additional 1 more members to the previous case. Therefore, a degree of internal static indeterminacy. The formula is m plus 3 minus 2j, where m is number of members. We add 1 more members from this previous case. Therefore, we have to get 18 members. Then 18 plus 3 minus 2 times of joint is 10. Then we will get the static indeterminacy. Internal static indeterminacy is equal to 1. The degree of external static indeterminacy can be calculated from this r minus 3 formula, where r is the reactive forces from the support. We have hinged support, it will offer 2 reactive forces, 1 roller support, it will provide 1 vertical reactive forces. Therefore, total reactive force from the support is 3, and 3 minus 3 equal to 0. The structure is externally determinate structure, but internally indeterminate structure. Therefore, the degree of static determinacy, external static indeterminacy plus internal static indeterminacy, then we will get 1. Therefore, this structure is called as statically internally indeterminate structures. Now look at this figure. We provide 2 hinged support. Therefore, each support will offer 2 reactive forces. Therefore, 4 reactive forces from the support. Therefore, the degree of external static determinacy formula is r minus 3. 4 reactive force from the support, 4 minus 3, then we will get 1. Therefore, the external static indeterminacy is equal to 1. But the structure is internally static determinate structure. Because we get the formula m plus 3 minus 2j, where m is nothing but number of members in the truss structure. It will be around 17 plus 3 minus 2 into joint is 10, and 2 into 10, 20. Then we will get 0. Therefore, the structure is internally static determinate structure, but externally indeterminate structure. Therefore, the total degree of static determinacy, we add these 2 values, we will get 1. That means m plus r minus 2j. Therefore, this structure is called as statically externally indeterminate structures. Then how, while doing the truss analysis, we can easily identify some of the members, which member are having 0 force members. If 2 members form a truss joint and there is no external load or support reaction at the joint, then those members are called as a 0 force members. Or in case if 3 members form a truss joint and there is no external load or support reaction at the joint, then 2 of those members are collinear, then 3rd members will be having 0 force member. Now look at figure 1. Then figure 1, joint A having 2 members, there is no external force from the support side as well as reactive force sides also. There is no external force or external loading as well as there is no reactive force from the support. It has only 2 members. Therefore, these 2 members having 0 force members. As well as the same, like if we consider figure 1, joint D having 2 members, there is no external loading as well as there is no reactive force from the support. Therefore, these member DE as well as DC will be having 0 force member. Then look at figure 2. If we consider joint D, there we connected 3 members, there is no external loading as well as there is no reactive force from the support. Out of these three members, member DE as well as DC having collinear members. Therefore, the third member will be having zero force member. It means the force induced the member AD will be having zero force member. The same like consider joint C also connected three members. Then member AC will be having zero force members because member CD as well as CB having collinear members. Therefore, the third member AC will be having zero force members. While doing the Truss analysis, we have made certain assumption. The first assumption is all the joints are pin jointed. It is loads only acting at the joints, and also the self weight of the truss member is neglected. So initially, the first step while going to finite element analysis, we have to derive the stiffness matrix. So let's consider a pin joint bar element as shown here for truss analysis. Due to load on the bar element, it will deform in the axial directions because the members carries only axial force. So due to application of this external loading condition, the member will be having axial displacement, where the axial displacement designated at node 1 is Q1, at node 2 is to be Q2. Then we have to, the horizontal displacement of your node 1 will be represented U1, and a vertical displacement is V1. So if you make a small triangle here, then we have to take a geometry properties, then we have to find out where horizontal as well as vertical displacement. So while doing the finite element analysis, we follow certain axis systems. One is to a global axis system. That means if we used a common axis, it will be used to indicate all the members in the structures. Then this reference axis called as a global axis system. Suppose if individual members can be referenced some axis system, maybe the axis placed at the end of this member, any side, left hand side or right hand side, then it is called as a local axis systems. Or if we place the local axis system at the mid of the member, whose magnitude of the axis varies from -1 to 1, then it is called as a natural coordinate axis system. So these three axis systems we are followed in finite element analysis. One is a global axis system, and second one is a local axis system. In this local axis system, if the axis placed mid of the member whose magnitude varies from -1 to 1, then it is called as a natural coordinate axis systems. Therefore, if you consider a individual member the truss, then we follow for a local coordinate axis system. Then it is look like a one-dimensional bar analysis. So we have used a local axis here, Mn. Then capital and XY, this indicates where global axis systems. According to the axis Mn, it is a local axis system. In this local axis system, the element having axial displacement with respect to the local axis Q1, Q2, with respect to X and Y is called as a global axis system. The global axis system, the node 1 and 2 having a nodal displacement U1, V1 as well as U2, V2. So let Q1, Q2 displacement of the nodes 1 and 2 the local coordinate system. Similarly, U1, V1 as well as U2, V2 components of displacement Q1 and Q2 denote in a global coordinate systems. From see the figure, where Q1 represents AC plus CD, where we have to consider the triangular ACB. We have form a right angle geometry form property. Then we will return as AC to be AB cos theta. Then CD can be written as a BD sin theta. That will be reference to U1 cos theta plus V1 sin theta. Similarly, figure 2, if we consider the triangle GEF, we can write Q2 is equal to EG plus GH, where EG can be referenced as EF cos theta plus FX sin theta, where EF can be written as U2 cos theta plus V2 sin theta. Then Q1, Q2 is a axial displacement with respect to your local coordinate system. Then U1, V1, U2, V2 is a displacement with respect to your global coordinate axis system. Now I have derived the relation between local coordinate axis system as well as global coordinate axis systems. So with this above equation I write in the matrix form, we will get Q1, Q2 that will be indicates your the nodal displacement in local coordinate system. Then we will get cos theta, sin theta, 0, 0. and 0, 0 cos theta, sin theta. U1, V1, U2, V2 that indicates your element of displacement as per your local coordinate systems. That will simply written in the matrix form. The matrix Q is equal to L times into del, where L is nothing but your transformation matrix. So the problem is related to truss in a one dimension when viewed in a local coordinate system. Because we place a local coordinate system, the individual element, then it is look like a one dimensional bar elements. We already derived the stiffness matrix for one dimensional bar element, that will be AE by L 1 minus 1 minus 1 1. We have to develop the element stiffness matrix in global coordinate system. Then we have to adapt a strain energy concept here. So the element strain energy in local coordinate system can be written as U is equal to 1 by 2. The displacement in local coordinate system is Q transpose into the stiffness matrix in a local coordinate system KL times Q. Then U is equal to 1 by 2 Q transpose KL into Q, where Q is nothing but your displacement in local coordinate system. We already derived the relation between local coordinate system as well as global coordinate system in terms of displacement. Then your Q is replaced by del transpose times of L transpose KL into L into del. Then we will get U is equal to 1 by 2 del transpose, where L transpose KL into L, it is indicates your stiffness matrix in global coordinate axis system, kg times into del. Okay, therefore kg is equal to L transpose KL into L. It will indicate your stiffness matrix for a truss element in global coordinate system. Therefore, we know that L transpose means cos theta 0, sin theta 0, 0 cos theta, 0 sin theta, into KL nothing but stiffness matrix due to local coordinate axis system, that will AE by L 1 minus 1 minus 1 1. Then L is nothing but transformation matrix. We already derived cos theta sin theta 0 0 and 0 0 cos theta sin theta. Then we multiply all those things, we will get your stiffness matrix for a truss element. Kg is equal to AE by L C square CS minus C square minus CS CS S square minus S minus S square minus C square minus CS C square CS C minus CS minus S square CS S square, where C is indicates cos theta, where S is indicates sin theta. Wherever we use C as in this slide, it will indicate cos theta as well as sin theta. Then we have to formulate our finite element equation. Let us consider a single element of your truss element. It is consist of node 1 and 2. The node will be having subject to a nodal forces. In horizontal direction is F1x and vertical direction is F1y at nodal location 1. Similarly, the nodal location 2, F2x and F2y. There is an axial force is F1 and F2. That will be resolved in two components, horizontal as well as vertical component. Then we know the finite element equation, K times del is equal to your applied force, and AE by L, your stiffness matrix for a global coordinate system, C square CS minus C square minus CS, CS S square minus CS minus S square minus C square minus CS, C square CS minus CS minus S square CS, S square times into your displacement vector due to in a global coordinate axis system. That can U1, V1, U2, V2 is equal to your nodal force in horizontal as well as vertical direction in node 1 and 2. That will be indicates F1x, then F1y, F2x, and F2y. This is for finite element equations. Then how we do the stress calculation? The expression of the element stress can be obtained by observing the truss element in local coordinate system is like a simple two force element as shown in figure here. Node 1 and 2, it is subject to only axial force. The force is resolved in two components, and only horizontal force as well as vertical force. According to Hooke's law, when a material is loaded within elastic limit, the stress induced the material is directly proportional to strain. This proportionality constant is called as a Young's modulus. Therefore, stress can be written sigma is equal to capital E into small e, where small e indicates your strain. That means change in dimension by original dimension. When you viewed in a local coordinate system, that the displacement node 1 and 2 will be a Q1 and Q2. That will be indicates E into Q2 minus Q1. Change in displacement, the respective original dimension of the member is indicates length L. Then sigma is equal to E into Q2 minus Q1 by L. That we will arrange it in the matrix form. Sigma is equal to E by L minus 1, 1 Q1 times Q2, where Q1, Q2 is nothing but the nodal displacement of node 1 and 2 with respect to your local coordinate system. Then we already derived the relation between the nodal displacement in local coordinate system as well as global coordinate system. That means Q is equal to a transformation matrix into your displacement vector in global coordinate system. Then we substitute in this equation E by L minus 1, 1. That is Q is replaced by your transformation matrix into your displacement vector in global coordinate system. It consists of node 1 and 2 having the nodal displacement with respect to x and y is U1, V1. Then nodal 2 with respect to x and y axis U2, V2. And we substitute, finally we arrive the stress equation sigma is equal to E by L minus C minus S CS U1, V1, U2, V2, where C is nothing but cos theta, S equal to sin theta. Then we try to solve this problem because we already derived the finite element equations. So the problem is the loading and other parameters of 2-bar truss element shown in figure. Determine, first thing is nodal displacement, second one reaction force, then third one the stresses induced in the elements. So given structures to be near 2-bar truss element. Okay, then I have first thing is we have to describe the structures. Here we have 2-bar truss element. I name the element number 1 as well as element number 2 for the given truss structures. Then we try to develop a finite element equation for truss element 1 as well as truss element 2. Then we have to assemble, we will get a global finite element equations. First we consider element 1. So the length of the element can be calculated from L1 is equal to square root of, because it is a element 1 is inclined member, they have specified horizontal distance as well as vertical displacement. We see this figure, the horizontal displacement is 750 millimeter and vertical height is to be 500 millimeter. So you use that one, we have to find out the length of the element L1 is equal to square root of 750 square plus 500 square, we will get around 901.4 millimeter. Then we have to apply your element stiffness matrix equation. Then K1 is equal to AE by L times of your matrix is C square CS minus C square minus CS, CS S square minus CS minus S square minus C square minus CS, C square CS minus CS minus S square CS S square, where C is in nothing but your cos theta. Then how we do the find out that value? Where theta is here, if you take any nodal locations, that will be theta measured from the angle between the positive x-axis to their respective members. If we consider, I take a reference as a nodal location 1, then we have to measure the angle in anti-clockwise direction with respect to a positive global axis. That will indicate the theta. We already know the horizontal displacement as well as vertical displacement, where horizontal distance is 750 millimeter. The vertical height is to be 500 millimeters. If we consider the triangular, then we have to use the tan theta. Tan theta is equal to opposite by adjacent, where opposite is 500 millimeter divided by adjacent is to be 750 millimeter. Then we will find out the theta value. Then we will get the theta value is equal to 33.69. Then we will get the cos theta value as well as sin theta value, where cos 33.69 equal to 0.83, sin 33.69 equal to 0.56. Then we substitute this given equation, then we will get our stiffness matrix for element number 1. So here, which node location with respect to, we have to find out the theta, that we have to the top, I written as the nodal displacement first. So suppose if you measure theta with respect to nodal location 2, then while assembling your stiffness matrix in the top, we have to return U2, V2, then we have to enter U1, V1. So here I found angle with respect to nodal location 1, therefore the top I reference say U1, V1, U2, V2. Then easily you have to assemble your stiffness matrix. Now I have developed a stiffness matrix for element 1. The same way we have to develop the stiffness matrix for element 2. So look at your element number 2. Then it is consist of node 2 and 3. Then node 2 will be having the nodal displacement U2, V2. The rest same. Node 3 will be having the nodal displacement U3 and V3. Then node element 2 having length is 750 millimeter. Then we have to measure the angle, that is a theta. This is measured from the respect. We take anyone with respect to nodal location 3 or with respect to nodal location 2. So here I measure with respect to nodal location 2. Therefore, we place the axis at a nodal location 2. Then we have to measure the angle with respect to positive x-axis. Then if we consider nodal location 2, then the angle theta is to be 180 degree. Suppose if we place the axis at a nodal location 3, then theta becomes 0 degree. Then if you find out that theta equal to 180 degree, then cos 180 degree is -1, then sin 180 degree is a 0 degree. Then we have to substitute the given stiffness matrix. Then we will get the stiffness matrix for element number 2. So once if we get the stiffness matrix for element 1 and 2, then we have to assemble your stiffness matrix. You see that we will get the stiffness matrix K2 values at 10 power 5 times 2.670 minus 2.670, then 0, 0, 0, 0, then minus 2.670, 2.670, then 0, 0, 0, 0. Suppose if you take the 2 as a reference node, we measure the angle, then the top I written is a U2, V2, U3, V3. Suppose if you measure angle with respect to nodal location 3, then the top red color we may indicate some U2, V2 means we have to reference here U3, V3, then U2, V2. Based on that, which nodal location we have to take as a reference node, we have to measure the angle, then top we have to enter first. So in this problem, I measured angle with respect to nodal location 2, then I written here U2, V2, U3, V3. Suppose if you measure the angle with respect to nodal location 3 means, then with the top we have to reference U3, V3, then we have to enter U2, V2. Then here I develop a stiffness matrix for element number 2. Now once we develop a stiffness matrix for all elements, then we have to assemble your stiffness matrix, then we will get global stiffness matrix. Then these were global stiffness matrix. Then how do that arrangement? We have to look at here the combination of U2, V2 is to be 1.27. Then how we will get this 1.27? We go for your K2, then U2, V2 combination. Here U2, then V2, the combination values is 0. Then if you go for element 1 stiffness matrix, then your U2, V2 combinations, that will be 1.27. Therefore, 1.27 plus 0, then we will get 1.27. The same way we have to assemble your stiffness matrix. Finally, we arrive at a global stiffness matrix. Then we have to formulate your finite element equations. What is your finite element equation? That means your stiffness matrix into your nodal displacement must be equal to your applied force. Therefore, it is your global stiffness matrix. Then what is your nodal displacement? So this given truss structure having 2 elements, then it consists of 3 nodes. Then node 1 having the displacement U1, V1. The node will be having U2, V2. The node 3 will be having U3, V3. So here node 1 and 3 having a hinged support, therefore it will offer some reactive forces in horizontal direction as well as vertical direction. That means R1x, R1y indicates the reactive forces from the hinged support at 1. Then R3x, R3y, the reactive forces from the hinged support at nodal location 3. Then if we consider node 2, there is some external loading will be acting in the vertically downward direction. That means F2y, the value is a minus 5000 Newton. Then we have to substitute, then we will get equation number 1. This is your global finite element equation. Once we get a global finite element equation, after that you have to apply your boundary conditions. So what is your boundary conditions? In this given problem, that a nodal location 1 and 3 having hinged support, it will offer 2 reactive forces at a nodal location 1, then it will arrest your horizontal and vertical movement of your nodal location 1. Therefore, U1, V1 must be equal to 0. The same way, node 3 also has a hinged support. It will offer 2 reactive forces. That means it will resist your horizontal and vertical movements of their nodal location 3. Then means U3, V3 also 0. Therefore, we apply these boundary conditions to your equation number 1. Therefore, we will get U1, V1, U3, V3 all are 0. Therefore, you neglect the respective rows and columns. Then we will get a reduced finite element equations. Then we will get 10 power 5, 4.58 with 1.27, 1.27, 0.83, U2, V2 is equal to 0 minus 5 times. This is reduced to a finite element equation once you are applied your essential boundary conditions. Right now I have two unknowns. From that I get two equations. While solving these two equations, we will get U2 and V2 value. Another two equations, 10 power 5 times your 4.52 U2 plus 1.27 V2 must be equal to 0. Then the 10 power 5 comes to that side, we will get 4.58 times U2 plus 1.27 times of V2 must be equal to 0. This is equation number 2. The similar way, 10 power 5 into 1.27 times of U2 plus 0.83 times of V2 must be equal to 5000. Then the 10 power 5 come to that side, we will get 1.27 U2 plus 0.83 times V2 is equal to minus 0.05. It is equation number 3. While solving equation 2 and 3, we will get the unknown values U2 and V2. Then U2 is equal to 0.029 millimeter, where V2 is equal to minus 0.105 millimeter. Once you have to calculate your all nodal displacement, then we have to calculate your reactive forces. So with these all nodal values, I am applying this equation number 1. These are finite element equations. Then we have to find out the reactive forces. That means here the right hand side R1x it will indicate must be equal to your first row into your displacement vector. Then we will get R1x value. Then your second row of stiffness matrix into your nodal displacement that must be equal to your R1y. Then your fifth row into your respective displacement vector must be equal to R3x, and sixth row into the nodal displacement must be equal to R3y. Therefore, we will get the reactive forces while just multiplication of your stiffness matrix into your nodal displacement and equating the respective rows. Then we will get R1x, R1y, similarly R3x and then R3y. Then how do we calculate your stresses induced in the element? We already derived the stress for truss element. That means stress induced the element is equal to E by L minus C minus S C S, where C is nothing but cos theta, S equal to sin theta. The respective element having node 1 and 2, that nodal displacement is U1, V1, U2, V2. The same way we have to measure angle with respect to global positive x-axis. So we already measure the theta is equal to 33.69. Then we get the cos theta value is equal to 0.83 as well as sin theta is equal to 0.56. We substitute in this above equation, we will get element stress minus 7.5 Newton per millimeter square. The minus sign indicates here the stresses induced the element is compressive stresses. Then same way for we have to calculate stresses for element number 2. And element number 2 consists of node 2 and 3. Therefore, the nodal displacement U2, V2 as well as U3, V3. This we multiple with E by L minus C minus S CS, where CS is nothing but cos theta sin theta. How do you find out your theta? Theta will be measured with respect to past x. If you take any one node, if you consider node 3 means we have to reference the top is U3, V3, then you have to enter U2, V2 value. Or if you measure with respect to here nodal display node location 2, therefore I reference U2, V2, then U3, V3 in your displacement matrix. Finally, we arrive the stresses induced the element 2 is 7.73 Newton per millimeter square. This to be a tensile stresses. So once you learn this lecture, we can address these possible questions. The first thing is what is meant by truss. Truss is nothing but a group of structural members are joined and welded together to carry only axial stress. The load acts only at the joint. All the members induced in the connected the truss element is a pin joint. It carries only axial force. And what are the different axis system followed in FEA? So there are three type of axis system following a finite element analysis. One is the global coordinate axis system. It means the common axis that can be used to indicates all the elements connected to the structures. Then another one is a local coordinate system. So it means the individual element that can be referenced with the help of a axis system, then it is called as a local axis system. Maybe the axis placed the mid, or maybe the axis placed at the end of the inside of the element. If you place the axis at the mid of the element whose axis magnitude varies from -1 to 1, Then this local coordinate system also called as a natural coordinate axis system. And question number 3, find out the static indeterminates of the truss shown in figure. Now, how do you find out the static indeterminates of the structures? For a truss element means, then we already gave some rule. There are two type of indeterminacy. One is a maybe the truss may be internal indeterminacy or external indeterminacy. For the external indeterminacy, then we can use that equation R minus 3, where R is nothing but the reactive force from the support. Here, joint A is a hinged support that will offer two reactive forces, but joint E having only roll support, it will offer only one vertical reactive force. Therefore, the reactive force from the support is 3, then 3 minus 3 must be equal to 0. Therefore, this structure is externally determinate structure. Then how do you calculate whether the structure is internally determinate or indeterminate? That we calculate from this formula, m plus 3 minus 2j. Where is m is nothing but number of members, where j is nothing but number of joints. By using this equation, then we have to find out the internal indeterminates of the structure. Then how do you find out the kinematic indeterminacy? I already told that kinematic indeterminacy is nothing but it is a minimum independent quantity is required to find out your displaced shape of the structure due to application of the external loading. Therefore, each node having 2 degrees of freedom, one is horizontal as well as vertical displacement. That is called as how many joint having into 2, then we will get unrestrained degree of freedom. Minus restrained degree of freedom means the reactive force from the support, it will arrest your horizontal as well as vertical movement. Suppose if we consider joint A having a hinged support, it will offer 2 reactive forces. That 2 reactive forces will be resist for vertical horizontal displacement of joint A. Then joint E having roller support, therefore it will offer 1 vertical reactive forces, it will resist for vertical movement of joint E. Therefore, 3 restrained degree of freedom. Therefore, total joint into 2, it will give unrestrained degree of freedom minus 3 restrained degree of freedom from the supports. Then we will find out your kinematic indeterminates of the structures. Question number 4, identify zero force member in the given truss structures. If any joint is considered only 2 members, there is no external force as well as R, there is no external reaction force from the support, then 2 members is called as a zero force member. Or if a joint consists of 3 members, there is no external loading, there is no reactive force from the support. Out of these 3 members, 2 members are collinear members, then third members will be having zero force member. So we investigate this figure, we see that joint C having connected with the 3 members, the member BC and CD are collinear members. Therefore, the third member EC will be having zero force member. And question number 5, the plane truss shown in figure is composed of members having square cross section 15 millimeter into 15 millimeter, and modulus of velocity E is equal to 16 gigapascal. The first question is assemble the global stiffness matrix. Then second one is compute the nodal displacement global coordinate system for the load shown in figure. The third one is compute the axial stresses in each element. So for the first of all, if we give any truss type structure, we have to give the numbering the nodal location as well as elements. So here there are 4 elements is there, 1, 2, 3, 4. Then we have to connected joints are 1, 2, 3, 4 joints are there. So each joint having 2 degree of freedom or horizontal and vertical displacement. Then we have to numbering the nodal location. Then you take individual element. Then we have to try to develop your stiffness matrix. Suppose if we consider element number 1, it is consist of node 1 and 2 means, then we have to develop a stiffness matrix along with your nodal displacement U1, V1, U2, V2. Suppose if we consider element 2 consists of node 1 and 4 means, then we have to develop your stiffness matrix along that U1, V1 and U4, V4. The same way we have to develop stiffness matrix for individual elements. Then finally we have to assemble, we will get a global stiffness matrix. Then we have to develop a finite element equation. That means K times into del must be equal to your applied forces. So that way the size of the stiffness matrix, how many nodal location we have, node 1, 2, 3, 4. 4 node is there. Each node having 2 degree of freedom. Therefore, the size of the stiffness matrix 8 cross 8. Okay. Therefore, what are the nodal displacement? U1, V1, U2, V2, U3, V3, and U4, V4. Along that, then your nodal forces must be equal to F1x2, then F4y. That means F1x, F1y, F2x, F2y, then F3x, then F3y, F4x, and F4y. So once you develop your global finite element equation, after that you have to apply your boundary conditions. Suppose if this here we have 2 hinge support, therefore it will offer horizontal and vertical reactive forces at their nodal location. Therefore, that respective nodal location, there is no horizontal displacement, there is no vertical displacement. Then we have to remove the respective rows and columns. Then we have to reduce the finite element equation. From that finite element equation, we have to find out your unknown nodal displacement. After that, we have to compute your axial stresses in the element. Thank you.